Time to move on to interval notation. This is a notation that we use when we write domains and ranges. And there are a couple of different sets of symbols we use. The brackets on the left are used when we include the numbers on the ends. The parentheses that are in green we use when we don't include the numbers that are in there. So for example, think of the brackets as a closed circle and think of the green parentheses as an open circle. Another way to think of the brackets would be something like a greater than or less than or equal to, while the parentheses would be just a strictly greater than or strictly less than. So I'm going to show some examples here of inequalities and how those inequalities look as an interval. So here's a simple inequality, x greater than 3. Now I'm going to write that using interval notation. Interval notation is a little more formal representation, and it is used quite often in calculus. So x greater than 3, we notice we have a strictly greater than sign. There's no upper limit to x, so it gets to go on forever and ever and ever and ever, consistently growing, but it can never be smaller than 3. It can never be equal to 3. So to express this as an interval, I have a parenthesis with a 3, indicating that's the lower limit or the lower bound. If you ever take a more abstract algebra course, you would call this a bound. In calculus, we would call it a limit or a lower limit. So we have a lower bound of 3. There is no upper bound. It just grows forever and ever and ever and ever, which would be infinity. Infinity is always a parenthesis because you can never equal infinity. You can never get there. It is not a number. It just simply means you keep growing faster, or if it's negative, you keep falling faster. So here is an interval for x greater than 3. And this helps us find numbers to plug in for x. So anything bigger than 3 with no upper limit. So this is an interval that shows all the possible values that x could be. And again, the parenthesis here means x cannot equal 3. Here's another example. Now we have x is greater than or equal to 3. Because x can equal 3, it's now a bracket. The bracket means x could equal 3. But it's still growing without an upper bound. And if this looks weird, well, it just looks weird. With intervals, we can have different symbols on each end. It just simply means we can equal this number, but we can never equal this. So when we have mixed symbols here, it means one side of that interval could be that value, the other side cannot. It can approach it, but it will never get there. Let's flip it around. Actually, let's just do both of these at once. X less than 3. Well, now 3 is the highest that x could potentially be. Here it cannot equal 3. So 3 in this case is now the upper boundary. It's the upper boundary. X gets smaller than 3. So that means it's going to negative infinity. In other words, I could have any number from negative infinity all the way up to, but not including 3. There is no lower boundary here because it says x is smaller than something. So there is no lower limit. It just keeps falling forever. It could be negative 3 billion to the 5 billionth power. That's certainly a number that fits that. And it could fall beyond that as well. There's no lower limit. So this interval is simply a reverse of this interval. Here, 3 was a lower boundary. Now 3 is an upper boundary. And the next one, we'll have the bracket by 3 because now we can equal that number. Or we could be less than the number. So here we include the 3. Here we do not include the 3. Here's an inequality that shows an upper and a lower limit. Let's look at that as an interval. So now x is between two values. Neither of these inequality signs is an equal to. So that tells me I have a parenthesis on each end. X can be anything between negative 10 and positive 3. Here's the interval notation for this inequality. Double parenthesis because x cannot be either of those values. This looks like I'm going to have a mixed notation. Bracket for the negative 10 because x could be that value. Parenthesis for the 3. So here's the interval, negative 10, 3. And sometimes we say negative 10 inclusive 3. Here's one that's a little more complicated. Now I have 2 inequalities. I see that I have my first one with the equal to sign just flipped around. But then I have a second condition here that could also be met. So this means that x could be between these two values, also including 3, or x could be anything greater than 7. So what's happening between 3 and 7? Well, we don't care because that's not part of our interval. So this is an interval or 2 intervals that have a gap between them. There's a gap between these 2 values. So here's how we express that. Here's the interval notation. Parenthesis negative 10. But a bracket for 3. Now I have a second interval. So the symbol that we use is a capital U, and that refers to union. Mathematical union means we're joining 2 things together, but you do not have to be in both. If there are more than 2, the union just means you have to be in at least one of them. Typically with sets, you will not be in more than one at a time. Sometimes you will be, but oftentimes not. So this U simply means union. We're going to join this with another set, and that is x greater than 7. So 7 with a parenthesis, and then there's no upper limit. So here is the interval notation for this statement. We have an interval from negative 10 to 3, with the 3 included. or union, we're joining this group with this group. X could be 7 or larger than 7 with no upper bound. It cannot equal 7. And then this is another way to show that once we get past 3, until we get to 7, there's a gap. If we were to graph this, there would be a gap in the graph. Here's another one that requires a union. X is any real number. X is the symbol for real number. X is any real number, but it cannot equal 8. So the way we express this is from negative infinity all the way to 8, we're good. But then at 8, we have a problem. So this first interval pauses when we get to 8. And then we join that union with a second interval that starts at 8 and goes to infinity. So this 8 is treated like a pause. We're good from negative infinity, so as far the most negative number we can think of, all the way up to 8, but then don't include it, stop. And then we start from there and continue onward. And we have to do it this way because 8 cannot be included in this, whatever function this is, whatever this graph will look like. 8 is going to be an asymptote or an open circle, or it is just not part of the graph. So we need to pause our interval here at 8, start over from that value, and do the next part. And finally, X is any real number. No restrictions. Absolutely no restrictions. X can be any number that's real. So X goes from negative infinity to positive infinity. This is interval notation. So if you need to spend a little more time understanding these examples, do that before moving on to the next part of this video. This next part, we're going to find some domains and ranges. And we write those domains and ranges using interval notation. If you didn't take my advice from a minute ago, do that now. We'll start with range. To find a range, the simplest way is to look at its graph. Range of a function can be easily found by looking at its graph. If you have memorized your types of functions, ranges are simple as well. For example, you know that a linear function has no restrictions on y values. So its range will be negative infinity to positive infinity. If you recognize that a function is quadratic, you know that the range will be from the vertex of that quadratic, and depending if it opens up or down, it'll be everything greater than that value or everything less than that value, and so on and so on. If it's sinusoidal, you know that it's going to likely be between -1 and 1, unless it's been shifted up or down. So knowing those functions is going to help you find a range as well. To find the domain, there's a few things we need to consider. Domain We're looking at all the possible x values, and our key here is, where is it undefined? If we can find where the function is undefined and take those values out, we're left with everything that x can be. And that's usually the way we go about this. We look to see what values give the function problems. If there are none, well, then the domain is negative infinity to infinity. If there are problems, that's where we'll need two or more groups of intervals. Here's things we look for: square roots or any even indexed root. We know that the inside has to be 0 or larger. Cannot have negatives inside a square root. When we are dealing with functions in this unit, we are not dealing with complex functions. So there will be no imaginary numbers. That's nice because that's going to help us with domains here. We know that everything that goes into a square root has got to be 0 or positive. The other thing we have to be on the lookout for fractions with a variable denominator. We don't care about a variable numerator. We care about a variable denominator. So I look for, where is the denominator going to equal 0? Because it can happen. Anytime the denominator is equal to 0, that gives us a problem that has to be dealt with. So those are the two main things we look for. Make sure the square roots are 0 or larger, and make sure denominators of functions are not 0. Now let's take a look at some examples of finding domains and ranges. I have several. Start with a piecewise function. Here's a piecewise function. Find domain and range. With a piecewise function, domain is simple. We are looking at the domain. All this stuff over here is going to help us with the domain. So let's start up from the top and work our way down. X is less than -3. X has no lower limit. No lower limit on x. So we know it's negative infinity. And that's good all the way up to -3. But I'm not going to write -3 and then a parenthesis, because hold on. -3 is included down here. So there is no gap. -3 is not used here, but it's used here. So we continue onward. We have no gap at -3. -3 all the way to 7, and then we stop. It looks like we have a gap at 7. Nope, 7 is used down here, and then x has no upper limit. So here's our domain. And if you're wondering, well, that just doesn't seem right, ask yourself, what numbers can't x be? You might say x can't be -3. Yes, it is. It can be. It can be -3 in this piece. So it's covered. Well, x can't be 7. Yes, it can. Down here in this piece, x can be 7. There are no gaps in the domain. We're looking for gaps in the domain. We're not looking for gaps in the function. This function will have gaps, but not in the domain. Not in the domain. There are pieces that this function is broken into, but every single possible x value is used. Now for the range. My advice for the range is to graph this. And if you're wondering to yourself, how in the heck do you graph a piecewise function? It's actually very simple, as long as we graph it in pieces. So here we go. I'm going to graph this piecewise function with my trusty calculator. So I start with x minus 3. But if I just do that, the calculator is going to graph x minus 3 for everything. It's not going to know that I only want it less than negative 3. So I have to tell it that. So I'm going to push parentheses. And then I'm going to go here to second. And then right here, where the math button is, you see the word test. Second math. And then you see some symbols. Actually, I have to get out of this because I messed up. First, I have to type x inside that parenthesis. Then I go to second math. And I see all these symbols here. So I have to go to number 5. Type in negative 3. Close it. And I have x minus 3. But then I'm telling the calculator, I only want that graphed for values that are smaller than negative 3. If you don't believe me, let me... Uh-oh. Something wrong. Something happened here. That does not look right. What happened? Time out while I do this. I might have to insert parentheses around both. Let's try that. Yep, okay. This is a different version than I'm used to. So we have to put the x minus 3 inside parentheses, then put the inequality inside parentheses. That tells the calculator, hey, only graph that much. So I can see that one, that it's going to graph x minus 3, but for x values that are only smaller than negative 3. So when x is negative 3, this is technically an open circle. X is negative 4. Negative 4 minus 3 is negative 7, and so on and so on. So put parentheses around both. The next part says, put a parenthesis, x squared plus 1. Close that. And now I have to do this, and your TI will not accept this as a valid entry. We have to do this separately. So type in negative 3, second, go into test. Here's my symbol, number 6, x. But then I have to tell it, hey, I have a second part to this. And again, if you just type in less than 7 right away, your calculator will ignore that. So we have to tell this in 2 parts. Negative 3 is less than or equal to x. Second, test. Now we cycle over to logic. Say, and, okay, calculator, there's one more thing. X, second test, is also less than 7. Close parentheses. So negative 3 is less than or equal to x. You could also type that in as x is greater than or equal to negative 3. And there's one more condition. X is less than 7. So now if I look at my graph, from negative 3 to x equals 7, it would show more. So if I trace that, tracing my x, trace. There we go. Get it on this one. X equals 7. Once I get above 7, you'll see that it stops. It's no longer accepting X values. It's just going to zero everything out. That doesn't mean it graphed that part. The calculator is just saying, hey, for this X value, I got nothing because you told me to stop. You told me not to go past 7. So it has to do something there. That's what it's telling you. These values are false. The 0 in this case means false. Nothing's there. Just like if I go back here, if I go to this first graph, the first part, x minus 3, here's x equals 4 point something. Yeah, got nothing because you told me to stop at negative 3. So those are the x values. There's the second part of our graph. Notice we have a gap here. There are no y values here. So we may have a gap there. Let's find out if that's going to stay true. 2x plus 3 is our third part. 2x plus 3. And then I have to go x into my test menu, greater than or equal to 7. Close that parenthesis. So now I should have all 3 pieces. And I can't see that piece because that's going to be off screen. So I'm going to make my window a little bigger. My Y max, I'll make that 20. See what happens. First part. There's the second part. And there's the beginning of the third part. Let me go a little higher. Change my window again. Let's make that 30. First part. Second part. Okay. So there we have it. There's our graph. So range is all the y values. Well, this will grow forever. This will grow forever. So any y value from here on up is covered. If I go across this part, all these y values are covered. Y values from here down are covered. Except for that one because it's an open circle. So we have a gap here. We have a gap. So let's put this all together. I'm going to pretend that negative 3 works for this function. What happens when x is negative 3? We get negative 6. But it's an open circle because we can't have negative 3 for this part. This shrinks forever, goes down forever, so all the y values to negative infinity are covered. All the y values to negative infinity are covered. Up to negative 6. Up to negative 6. If x was allowed to be negative 3 for this function, this would be negative 6. But it can't be. It's open. Then we have a gap. There are no y values between negative 6 and in here. Here, we have a y value of 0. It's part of this partial parabola. So starting at 0, we go all the way to infinity. Union includes 0 all the way to infinity. And we know that we go all the way to infinity because this piece right here grows forever. And it's linear. 2x plus 3 you have to recognize as linear. Linear functions rise or fall forever. So that's going to go all the way up. All of these y values are covered, and this one grabs all of those as well. So there's our range for this piecewise function. Any x value can happen, and our y values are pretty much everything except between -6 and less than 0. So there's a gap here of y values not being used. Let's look at another one. Here's another piecewise function. Find the domain, find the range. Again, the domain we will get just by looking at the conditions here. X is less than 0. Falls forever. Comes up to 0 and stops. Notice in the last one, we stopped at -3, but then we picked up at -3. Here we stop at 0 and pick up at 1. So I need to close this interval. Union. Now I pick up at 1 with a bracket. And I go up to 5. And then I check the next place and we start at 8. So here's a second gap. Close that one with the bracket. And then we have another union. And then we have x greater than 8. So not including 8, parenthesis, all the way to infinity. So 3 pieces, and each piece gets its own unique interval because we have gaps in our x-axis. We have gaps in our domain. Let's find the range. I'll graph each piece. X over 2. X over 2. Keeping my parenthesis. I shouldn't have to change too much here. Change that to a 2. X still less than. I just need to make that a 0. Okay. The next part says 3 minus x. I can delete that part. 1 less than or equal to x, so that's good. And x, I need to change this symbol to less than or equal to. And then change that number to a 5. And then the bottom part says x squared minus 1. And change this to strictly greater than 8. Okay. I have all my pieces here. Let's graph it. And I can't see the top part because we're starting with 8, so that's a huge y value. Let me change the window. Let's make that 70 so we can at least see a little piece of that. And there we go. Okay, so we have a huge gap from here to here. Huge gap in the y values. This, again, x over 2, that's 1/2 x. We need to recognize that as linear. That's going to come up here to 0, starting at 1. This y value starts at 2 and comes down. So I'm going to zoom into this part right here. I know I'll deal with that one in a little bit. I want to zoom in. Go to zoom, number 2. I want to zoom into this area. That's not the area I wanted to zoom in on. Let me do it this way. I'm going to do number 6 to zoom in on what's going on here around the origin. Looking for y value. So I have every y value up to here. This overlaps all of these y values, and then it adds some more here. So I need this very top point. And that top point is when x is 1. When x is 1, y is 2. So I have every y value from negative infinity to 2 covered. Union with. Now we have this huge gap. Huge gap. So I need to know where the next set of y values starts. And that's going to start, change my window back. I want to make y max, let's say 80. I'm going to make y min 50. So we can get a little focus, a little better focus on where this starts. Right there. I want this bottom point, this minimum point. So there's no little curve here. It's just starting here and going up, straight up. If x was allowed to be 8, y would be 65. So I imagine there's an open circle here at y 65, and we're going up from there. It's not allowed to be y equals 65 because x is not allowed to be 8. But that's our, I said 60. I keep saying 65. It should be 63. It should be 63, not 65. We're subtracting 1, not adding 1. 63 is our beginning. 63 is our beginning. So if x was allowed to be 8, y would be 63. But x is not allowed to be 8, so y cannot be 63. That's why we put the parenthesis. It gets really, really, really close as this falls. It gets really, really close to y equals 63, but it never gets there. So there's our range for this function, this piecewise function. Let's look at some more examples. These we're only going to find domain. Domain only for these. Here's a square root. We have to ask ourselves, what can go in a square root? Any positive number? I can take the square root of a positive number. I can take the square root of 0, but I cannot take the square root of a negative. So I have to ask myself, what value of x makes this square root 0? 0 is a transition between positive and negative. So I will set the inside equal to 0 and solve. Okay? X is negative 3. Now I have to ask myself, which side of negative 3 do we want? Think of negative 3 as the boundary. If I plug in a number to the right of negative 3 and I plug in a number to the left of negative 3, one of those answers will give me a positive, one of those answers will give me a negative. So what's an easy number to the right of negative 3? And I hope you said 0. 0 is an easy number. Plug in 0. Do you get a positive or negative for the square root? Of course you get a positive. If x is 0, we have the square root of 3. So all the values to the right of negative 3 will give us a positive square root. So our domain is this, negative 3 to infinity. If I plug in negative 3 for x, I get the square root of 0, which is 0. If I plug in negative 2.999, I get the square root of 0.001. Still positive. If I plug in negative 3.01, that's a number to the left. Oh, I get the square root of a negative, and that's not allowed. So here's my domain. Here's another one. Square root of 9 minus x squared. I'll do the same thing. Set the inside equal to 0, solve for x. Positive 3 or negative 3. And now I'm going to make myself a little number line. Here's negative 3, here's positive 3. I have 3 areas I have to look at. I know if I plug in negative 3 and if I plug in positive 3, I get 0. So now I have to look and see where my positives and negatives are. So I'm going to pick a number to the left of negative 3. Negative 4 is to the left, and I'll plug negative 4 in for x. 9 minus negative 4 squared is 16. 9 minus 16 is a negative number. So anything to the left of negative 3 gives me negative. That's bad. Pick a number between negative 3 and positive 3. Again, things simple. 0. Plug in 0. Square root of 9. That's positive. Pick a number to the left, or sorry, to the right of 3. Pick a number to the right of 3. How about 4? 9 minus 4 squared. 9 minus 16. That's a negative number. I'm looking for where I have positive values. And I know I include that and I include that because I can have the square root of 0. So here's my domain. Negative 3 to positive 3. Anything else is out of bounds. Those are the only numbers I can plug in for x. Any number between negative 3 and positive 3. Next example. Same thing. In fact, this looks like the same exact problem. But it's not, because notice we've switched the order of subtraction. So now when I make my little number line, I include those, I include those. When I pick a number to the left, here I'll pick negative 4, 16 minus 9, now that's positive. If I pick a number between them, zeros between them, 0 minus 9 is negative. And if I pick positive 4, number to the right here, that's positive. So now my domain has changed. Switching the order has changed my domain. Negative infinity all the way up to negative 3. Now there's a gap. Positive 3 all the way up to infinity. So in number 2, our domain was just this little gap of numbers here. Just this little space of numbers. In number 3, our domain is all of this and all of this. It's everything except the stuff in between. A few more examples. Let's look at some rationals here. We have no square roots in this one, but we have a variable in the denominator. We know that the denominator cannot equal 0. So let's find the value that makes it 0. It's negative 1/2. We cannot have x be negative 1/2. That's the only number that fails. So I start from negative infinity up to negative 1/2. And then we have to jump over the asymptote. Start at negative 1/2 again and continue on to infinity. That wasn't so bad. Let's make it more interesting. Same deal. I know that x cannot be negative 1/2, but I also know that the square root has to be positive or 0. So we have two things to consider here. I know I can take the square root of 0, but that square root is in the denominator, and the denominator cannot equal 0. So this number is now a problem. That denominator not equaling 0 takes precedence over the square root of 0. So we cannot have negative 1/2. In addition, I'll put an open circle there. I need to know where the square root is positive and where it's negative. So I need to pick a number to the right or the left. I'll pick a number to the right. Pick a number over here. An easy number, 0. Plug 0 in. Do I get a positive or a negative? It's positive. So that means all the numbers to the left of this should be negative. If I plug in negative 1, get negative 2. Negative 2 plus 1 is indeed negative. So here's my domain, putting all this together. Thought I hit red. Here's my domain. It's not negative infinity because none of these numbers work. I start at negative 1/2. But negative 1/2 makes the denominator 0, so it's out. No upper limit. Negative 1/2 to infinity. It is not a bracket because negative 1/2 works for the square root, but it does not work in the denominator. It makes the denominator 0. That's why it gets a parenthesis. Let's make it even more interesting. So I have my square root, 2x plus 1. I know that has to be 0 or a positive, but I also have a denominator. So again, negative 1/2 works for the square root. It does not work for the denominator. Open circle. And I need my denominator, I need my square root to be positive. Well, we already did that one up here. We did that one. So essentially, we have the same domain. We have not changed our domain. If I plug in anything bigger than negative 1/2, I will be able to take the square root of that. And as long as I don't plug in negative 1/2 anywhere, I get a denominator that works. So here's our domain. As long as I don't plug in negative 1/2, anything bigger than that can be calculated. Same domain. Two different functions, same domain. Last one. Denominator cannot equal 0. So I know x cannot equal 5. I also know that the square root has to be positive. So when x is 3, the square root is 0. And now I look for my positives and negatives. 3 is okay. 3 is an open circle. Now I look for my positive and negative. To the left of 3 is 0. If I plug in 0 for x, problem. All these values are negative, therefore all those values are positive. But hold on, 5 lives over here. X cannot equal 5. So we have to be careful with our domain. Square root part starts at 3. 3 is okay. 3 also works in the denominator. And we're good until we get to 5. 5 is a problem. 5 works in the square root, but not in the denominator. Union. Now we start at 5 and we go on forever. There's the domain of that function. Study these examples thoroughly, carefully, make sure they make sense, and make sure you post any questions that you have on this.